All right. Hello, everybody, and welcome to this week's GBO Colloquium talk. Today, I have the pleasure of introducing Jordan Guerra, who is working at Villanova University. And today, we'll be hearing about his work using HAWC Plus on SOFIA in order to better understand magnetic fields. So take it away, Jordan.
Thank you, Jesse. I want to thank the opportunity of talking to you guys today. We now have here at Villanova one of your, former colleagues, Natalie Bottlefield, and she mentioned this opportunity, and I think it's great. Today, what I'm going to be talking about is basically a little bit of there's a little bit of basically two major work that I've done that I have contributed to involving SOFIA HAWC plus polarimetric data. Okay. Honestly, I will say, if there's anything that comes up that you absolutely want to, require some clarification, you want to ask, right in the moment, I don't have a problem with that. But if we save the questions to the end, it's fine as well. Okay, so as I mentioned, what I'm going to be talking about here basically consists of two main works that we did in regarding the Orion Molecular Cloud Region 1, and also the Starburst Galaxy M82. Okay, both of them, completely, based on HAWC plus data. And I also want to mention a little bit of, what direction we're going in order to fully utilize the HAWC plus data in order to, advance and better understand the role of magnetic fields in astrophysical observations. Okay. So just a quick sort of introduction to what HAWC plus on SOFIA does. Many of you probably know that SOFIA is it's an airborne observatory. Its plane has a 2.5 meters telescope, and it flies higher than regular commercial planes in order to avoid most of the water vapor in the atmosphere to observe in the far infrared range. Okay, so in particular, HAWC plus is I believe one of the newest instrument, and when I say newest, it's still within 5 years, I believe, and it has the capacity of observing a polarization of dust polarization in the far infrared ranges. It has currently 4 working bands. You see here in this table, from A to B. Band from A to E. I'm sorry. Band B is I believe it saturates, so it's not commonly used. However, sometimes it's offered. But the working bands that most people work with correspond are centered at 53, 89, 154, and 214 microns. Okay, these bands have values of beam size that goes from almost 5 arc seconds to 90, almost 18 arc seconds. And actually, HAWC plus works in 2 observation modes: a scan mode and chop mode. The most traditionally used to observe polarization data is the chop mode. However, we have started SOFIA has started offering the scan mode for polarization as well, which increases the efficiency and how fast you can basically reduce the observation time for any target, which is fantastic. And just to give you an example, this map that we have here corresponds to the polarization observations in of 53 micron, my bad, here I'm saying 89. For the OMC one, this is one of the 4 maps basically that we use to, that I will be referencing in the first part of the talk. And basically what, traditionally, because this is dust polarimetric data, we know that the dust aligns themselves in molecular clouds with the magnetic field direction, and therefore the polarization direction of the direction of the polarization of vectors, the rotated one, tell us in what direction the magnetic field, or in what orientation the magnetic field is in the certain cloud. Now, that traditionally the polarization data, as I mentioned, just give you this general orientation of the magnetic field. But what we actually want to do, which is it's from basically observing the patterns of the polarization vectors here, is to extract the magnetic field strength. Okay, so for that, it has been used for a very long time. Actually, it's been around since the 50s. It's this method called the Davis-Chandrasekhar Fermi. This method basically it results from assuming that what you observe in the polarization vectors pattern is it's the result of establishing of an Alphen wave existing moving along the magnetic field lines. Now, what the method basically requires in this case is that any deviation from the magnetic field is this continuous lines here is the large scale magnetic field, and then the polarization vectors here will deviate a little from those magnetic field lines due to the presence of turbulence at smaller scale. Now, what the DCF method, what utilizes is basically says that the velocity of that Alphen wave is proportional to how much what is the dispersion, the dispersion in the velocity due to the turbulent motions, and how much these polarization vectors of the magnetic field deviate from the large scale due to the turbulence. Now, we know that the Alphen wave velocity is proportional to the large scale magnetic field, and therefore, you can arrive to this expression here of the planar sky. Okay, where normally in order to use this expression, we have to assume that the turbulence is isotropic, so you can use the dispersion of the velocity dispersion along the line of psi to in this expression, which gives you only the magnetic field component in the plane of the sky. And to utilize this expression, you need to know or have some information about the mass density in the cloud. Now, one of the main caveats in this expression is that, as I mentioned, this sigma phi value that we have here, which correspond to what we will call as the angular dispersion or the angle dispersion, has to be only the contribution of how much the vectors deviate from the large scale component, and not it cannot contain any information of dispersion due to the large scale of the magnetic field. In order to address that, okay, a method was developed by Martin Hood in early 2010 that basically constructs this function here, 1 minus the cosine of delta phi as a function of L. This function is a form of a structure function that basically looks at the difference between a pair of polarization vectors. Okay, what is the difference in angle between these two guys, and characterizes the difference between these two, a pair of polarization vectors that are separated by a distance L, okay? And then you just basically calculate the cosine of that quantity, and then being the function in by values, being this function for certain values of L. So there's no dependence on, like an angle in the plane of the sky. Now, this function, which is measured from polarimetric data, can be described by this expression on the right that has two components. First, the term that is proportional to L squared, the distance. It characterizes basically the contribution to the angular dispersion from that large scale magnetic field structure that I was mentioning before. Therefore, this term here doesn't give us any information about the turbulence. And then the first term, this huge term that we have here, tell us it's that term that contains the effect of the turbulence, which happens to take place at a small scales in L values. This expression basically takes into account that the turbulence is Gaussian in form, and that the correlation or the form of the autocorrelation of this function, basically this form, has a wave that is due to basically the turbulence correlation length and also the observation beam size. So basically this expression takes into account the fact that your observations having a beam size W, also sort of that smooth, smooth to a certain extend your polarization information, which results on also smoothing the turbulence component, and also takes into account the integration along the line of sight, because your polarization data also results in an integration basically of along the depth of the cloud in particular. Now, when we construct this function and fit it with this function in particular, what we can do then is, after a really long derivation, is that you can approximate the angular dispersion as this value, this ratio here, which corresponds to the ratio of turbulent to large scale magnetic field energy. And then you can evaluate this, the DCF expression, basically. When we apply this method directly to the OMC1 data that we got from HAWC+, okay, the first thing that we notice is that the data has so much angular resolution that we could actually do a little more detailed analysis. And when we look at the OMC1 region, we say, okay, there is 3 clear morphological regions here that are different. How about we separate it and we apply the DCF method in this way? And what we found was that in this region that we call the BNKL, because of the presence of that object, we found a magnetic field that was in the order of 1 milligauss, while in this H2 region and the so-called bar of the OMC1, their values were about 1/3 of that. Now, so we found that these 3, within the OMC1, there is this 3 different regions giving us different magnetoturbulent states. Therefore, we thought it was natural to perhaps, wanted to go even deeper in details and see if the polarimetric data would allow us to still have, the statistical level to just construct maps of the magnetic field strength rather than just having average value over certain regions. So the approach that we took for this was relatively simple. We, for example, asked the question, okay, if I center in this position, for example, I can define a kernel around this position and then construct my dispersion function with all the vectors that are inside that circular kernel. And then you can see here on the right the resulting dispersion functions for these three positions here that correspond to these three regions, B and KL, H2, and the bar. And then basically you can, using some function like chi-square or correlation, basically you can find which size of your kernel will fit that model that I presented before better by reducing, your metric. That then will provide us basically, with an information of this ratio of magnetic energies I presented before for each position or pixel in your data. Of course, taking into account or keeping in mind that because you use the information around it, that it will be correlated to a certain radius. Now, the way that we solved this was basically we had to solve the fitting of the magnetic of the correlation function, remind them down here, and for each pixel. So we put this through MCMC method, a solver, and let it run in one of that small cluster that we have here at Villanova University, and found best or the best fitting models for each case. This example that I have here correspond to the three fitting parameters that we don't know from this expression, which is the ratio of energy, this delta value, which tells you the correlation length of the turbulence, and this parameter that characterizes the large scale contribution. For the purposes of using the DCF method, we mostly care about the ratio. However, the other two quantities are important as well. But we're gonna, concentrate on the use of this ratio. Well, now once we have constructed maps of this ratio for each one of the bands that we have, okay, and in order to construct a map from this information we have, we also need to know or have a map of what sigma v will be, the dispersion velocity, and the mass density. Now, for the mass density, we have we can construct it by knowing the column density, which was found by doing spectral density fitting per pixel, and you have to assume all the terms on how what's the depth of the cloud in order to transform that into a volume density. Now, for the velocity dispersion, we use observations. We use ammonia observations, actually from the Green Band telescope, part of the gas survey. And yes, because basically the ammonia data traces very well the dust, at least in dense parts. So the problem here is that these three maps, in order to combine, have different resolution, angular resolution, and they have to be basically put to or smooth to the one that has the largest one in order to combine. When we do that for this particular example here, we ended up with this map of magnetic planar scale magnetic field strength with a resolution of 77 arc seconds. Okay, when we do that for all four of the polarimetric data that we have, these are the results. And we see that not only going down in resolution gives you stronger magnetic fields, but it also starts showing you slightly different characteristics. So, for example, here at 89 micron, you see this cavity very near of the BNKL object that is not visible in the band D and E, and that actually we call cavity because the magnetic field strength decreases there. And we speculate that basically closer or in this area, the polarimetric data might be tracing a warm dust that is probably deeper into the cloud. But this so far is just a little bit of speculation. Now we don't basically discuss much the 53 micron here, because the problem that we have is that the 53 micron loses a lot of the details that were obtained from the polarimetric data, because it had to be smooth out to higher resolutions. And that's why we see that, for example, this cavity here doesn't quite appear very well in the 53 micron, and the magnetic field strength decreases compared to the 89 microns. All right, so that's for the magnetic the planar sky component. Now we also wanted to explore a little bit whether the same polarization data could give us information about the line of sight component. Now, we tested, we tested a different form of dispersion, calculated as this S value here. Basically just measures a form of variance around a central value, a central value or an average value, okay? For which you have to basically set a circular region to calculate. This allows us to calculate, a map of S value like this one in this map here. And some authors have actually proposed the idea that this form of dispersion, or we call it local dispersion, is dominated by the angle that the magnetic field forms with the line of sight direction. If you can assume then that this power law is true, you can, just by knowing basically splitting the vector magnetic field into components of the line of sight and the planar sky, with calculating this S map, you could potentially just correct the planar sky magnetic field, and in order to approximate the line of sight. The other thing that we notice is that when you take the Seaman measurements and overlay it to this map of the local dispersion, you see that there might be a spatial correlation in which larger values of this S parameter, this dispersion, might be correlated with larger values of Seaman measurements, at least in absolute value. But it's not really a linear correlation. So we wanted to explore this power law in particular. In order to do that, basically we just use the polarization data to feed for this polarization data and the Seaman measurement to feed for these parameters A and the exponent N, and correct the planar sky magnetic field strength in order to obtain the line of sight component. These maps that I show here have, interesting or has some caveats in it. First of all, the assumption that these dispersions is dominated by the magnetic field direction with the line of sight is it's very important, because they can be other effects that are contributing to this form of the dispersion, such as how much the magnetic field is canceling along the line of sight. So that means the magnetic field can be really tangled along the line of sight, and that will also contribute to this this measurement of S. Now, the other thing is that we only have very few values of the CMAM measurements, therefore our fits are not, have really large errors, and there's pretty clear covariance between the plane of sky component and the line of sight component. The reason why we wanted to, explore this path is because we wanted to really construct maps of m/phi mass divided by the magnetic flux that are a little more accurate than only considering one component of the magnetic field. We know that these maps in particular will tell you where in the cloud you have supercritical or subcritical regions, supercritical regions in which gravity dominates, and are the places where a collapse due to gravity will likely happen, and therefore a star formation begins. So the results that we got here, we see that along the filament, we see really clear supercritical regions, and that this supercritical region seems to be a little perpendicular to the direction of the magnetic field, which is consistent with the results from the Planck team. All right. So, the conclusions that we arrived from this study was that, the HAWC data has enough resolution to basically go from average values to maps. We can basically apply the DCF plus dispersion analysis in a kernel size and move it around and then construct maps. We think that the local dispersion might contain some information about the line of size, but this needs further testing, especially using MHD simulation, and perhaps using observations that have a more richer CMAM measurements. And what we really believe is that maps of m/phi will be very useful for studying, molecular clouds, especially to determine which parts of the clouds might form, might end up, in forming stars. But this will be part of the future work. Now, the second part of this talk, which I might have to rush a little bit, correspond to the M82 galaxy. This is a starburst galaxy, okay? And when it was observed by HAWC in 53 micron, they observed that at the core of the galaxy, the magnetic field strength, the magnetic field direction looked very perpendicular to the plane of the galaxy. So, and when this galaxy was observed at other wavelength, you can clearly see these outflows of material just like traveling really fast and reaching distances, very large compared to the core or the starburst core. So when you look at this picture, you think of a few questions. One of them is like, okay, if you have flow or relatively fast flow and magnetic field, what's the interplay between these two guys? And also, when you look at the magnetic field direction at the core, which might hint at a colloidal geometry, you also want to know if this magnetic field might also extend in a very colloidal geometry at larger distances. And if that is true, and that resembles a little bit like the field lines of like a barn magnet, do the magnetic field lines, turn around and come back and provide some form of feedback into the core of the galaxy, or are they actually open? So in order to do that, we took 3 steps. The first one was to calculate the magnetic field strength in the core. But the problem with this one was the fact that there is the presence of this large scale flow. And we had to find a way to modify the DCF method for the presence of this large scale flow. So we study a little bit the equations, especially we see that the alpha and wave velocity will be modifying this way if there is a background flow. And when you include that effect into the DCF approximation, you see that then the magnetic field strength will be reduced from if you don't consider that there is a large scale flow happening, in the plasma. So the second step is we look at the global balance between the gas energy and the magnetic energy. So we calculated the turbulent plasma parameter called beta prime, which takes into account the kinetic energy and the hydrostatic energy of the gas, and divided by the magnetic energy of the magnetic energy. And when we calculated this for average value, we find that the magnetic energy actually is 2 times larger than the gas energy, which means the magnetic field is dominating the dynamics, at least in the core region. Now, we use this expression actually to construct a map of magnetic field by basically knowing that we can construct, we have a map of kinetic and hydrostatic energy through knowing, basically having a map of mass density and velocity, and use the global beta prime as to basically scale the resulting magnetic field strength. And this is what we see in this map, which at the very center of the core can reach magnetic field strength of up to 1 milligauss. Now, why do we wanted this in particular? Because in order to solve the problem that if the magnetic field lines are open or closed, we borrow a technique from solar physics that basically says that if you know the magnetic field at a boundary, and you assume conditions at a different boundary, you can find or extrapolate the magnetic field structure everywhere by basically assuming a few things. Like you can assume the magnetic field is completely free of force, its potential, and things. And yeah, there's like potential, then it's a force free, then there's linear force free, and then fully will be non-linear force free. But for this simple case, basically, if we choose one of our boundaries to be at the plane of the galaxy, we can use the direction given by the polarization vectors and the strength given by the map shown before. And all that we have to do is solve this Laplace equation, in which phi here is the scalar potential with these boundary conditions, and assuming that B has to vanishes at infinity. If we do that, then what we find is that the magnetic field, of course, is calculated just as the negative gradient of that scalar potential. And we see that in the core of the galaxy, the magnetic field actually matches very well here. The potential field is in red, and the original HAWC plus data is in black. You see that for most of the core, it really matches very well, except for areas like this one here and this one here, which are a little away from the plane of the galaxy and the center of the core, in which effects like galaxy dynamics might be dominating there. But in this region, the magnetic field seems very potential by comparison. So if you basically extend and look at the field lines at much farther distances, you see that they do behave in a very colloidal way. Okay. Now, the important thing here is that in order to see or determine whether the field lines will be open or closed, you have to look at the balance between magnetic field energy and the gas energy at, different larger distances. So from our model, we determined that at a distance of 6.6 kiloparsecs in radius from the core, the magnetic field has a strength of 15 microgauss, right? From different observations, we find that this of course produces an energy of the order of 10 to the negative 12 grams per second square per centimeter. Well, from different observations at the same distance, you calculate a kinetic energy of the gas, and you see that it's 2 orders of magnitude larger than the magnetic energy. In this case, what you see is that the gas at this distance has larger energy, allowing the particles traveling at that velocity to basically not feel the attraction from the magnetic field lines anymore and just simply continue traveling. That means that if a particle starts traveling along a magnetic field line at the core, it will travel basically along the magnetic field lines up to a distance of 6.6 kiloparsec, in which it can just basically break from it and travel, without restriction. Now, what do we find here from this study is that in the starburst of the M82 galaxy, the energies are not so different. We're talking about twice the magnetic energy to the gas energy, but it's not several orders of magnitude, one dominate over the other. But the magnetic field has a larger role to play. Therefore, the flow from the core will follow, the magnetic field lines. And we determined that then at large distances, a colloidal structure of magnetic field lines is most likely. And this, of course, is basically making a channel or a highway for this material that is produced at the core of this starburst galaxy to basically become part of the intergalactic medium. Now, as a part of the ideas of where do we want to go from here? Of course, the core of this work is based on the DCF method, and the DCF method has a handful of known biases or assumptions that we want to study and determine whether we can basically calibrate the DCF method in order to give us better estimates of the magnetic field strength. And for that, we want to use MHD turbulence simulations to study several of these biases or assumptions. Now, there is a project called the CATS or catalog for astrophysical turbulence simulation. This provides a relatively large amount of data publicly for use that we will start using to achieve this calibration of DCF method. So basically, what we want to is to take this cube of MHD simulated data and construct polarization data, or what we call synthetic polarization data, something that looks very similar to our observations. For that, we basically have to construct maps of stock parameters R, Q, and U, from which we can calculate polarization fraction and angles. These, by the way, are very preliminary results, and they're still going through a series of tests, but it's just meant to kind of illustrate and get a conversation going. Now, once we have data like the polarization fractions and angle, we want to then make it look much more like the HAWC plus data, because at the end of the day, if we're going to calibrate the DCF methods in order to use it with the observational data that we mostly work with, so we can change the resolution of these maps to be closer to one of the bands on HAWC plus data, and then from that we can actually put it through our pipeline of doing the dispersion analysis and the DCF. And when we do that, okay, we realize that what we are actually obtaining are several orders of magnitude higher than the reference value. So this could actually be this is, for example, this is one example of what I will what resulted of using this simulated data. And of course, I mean, looking at 400 milligauss is something very large, but it is actually 23 times larger than what you will get from the actual simulation. And it reduces a little bit if you in particular use the correction for the large scale flow. But the point here is that we might actually be needing more a correction to the DCF approximation depending of the specific setup of this MHD simulation. And we are just studying this at the moment. Now, we also want to extend this map making strategy to more objects, and we got assigned some time on SOFIA to observe molecular clouds in the GBO, for which we have NH3 data from you guys, and we want to match those regions and observe these maps of magnetic field strength in these objects that have, that belong to this common region. SOFIA has started observing some of these, but we don't have resulting maps yet at the moment. Now, this is one of the examples of what I was mentioning, what could be done by having maps of M/5, for example. And this could, M/5 could really be used in tandem with things like the histogram of relative orientation, which basically compares the direction of the magnetic field given by polarization data with the gradient of a mass, or the column density, basically. And if you basically look at the statistic of those direction in particular, and you look at the evolution of that with that parameter M/5, you can, the parameter of M/5 has a really clear boundary on where magnetic field dominates, or gravity dominates, or mass dominates. And then you can start making clear conclusions of whether there is a preference, direction, or alignment between magnetic field and the filaments when it's dominated, magnetic field dominated or gravity dominated. Finally, some of another thing that I am looking into, also borrowing a little bit from solar physics, is that there is a way to basically determine that the actual direction of all these headless vectors that we have that we use when we work with polarization or polarimetric data, but basically minimizing an energy function that takes into account the current and the divergence of the magnetic field. This is very preliminary, but I think it could definitely be used with the magnetic maps, or magnetic field strength maps that we construct, and the polarization data from SOFIA. Well, I mean, it seems like it took more than I imagined, but that's all I have to present right now.
All right, fantastic talk. Thank you very much, Jordan. And especially thank you for giving us a look at what honestly seems like a very sticky topic of magnetic fields. So unfortunately, we can't give you a physical round of applause, but a virtual one. And at this point, I'd like to open it up to the audience. If you have any questions, please feel free to unmute yourselves, and or if you prefer to write in the chat. But I will start things off just by saying more of a comment. It seems like this method, with the exception of the assumptions you make at the beginning, can be applied to most any regime, any type of environment with magnetic field.
Well, that is an interesting question, because, so for example, the DCF originally was just applied to basically any polarimetric observation that you have, if you can quantify the dispersion in this polarization vectors, and density and velocity dispersion. You say, okay, I can approximate, I can use the DCF. However, you start clearly doubting a little bit of not being not having trust on the method when your observation has clearly the influence of another phenomenon, like large scale flows, shear flows, perhaps a very specific configuration. Then that was basically what it motivated for us to study a little bit this how it will modify the DCF approximation, this specific situations, because you can see it from a point of view that if you obviously situations like flows in general, shear flows, large scale flows, will modify the propagation of an alpha wave. And that's the approximation from which we're actually, deriving the magnetic field or the DCF expression.
Right. Okay. Thank you. All right. And are there any other questions in the audience? I know it's for someone who doesn't study magnetic fields, it seems like a scary topic, but anything that you want to ask of Jordan, you are welcome to do so.
Jesse, can I ask a question?
Absolutely. Go ahead, Larry.
So it's not something I'm particularly familiar with, but I was wondering if you could comment on the Laserian and Burckhardt methods of comparing velocity gradients to magnetic field propagation.
Yeah, the comment, and I apologize for this, is basically, I have not had the opportunity to really work with that one. However, I am very aware of it, and it basically depends on who do you ask. They will tell you whether they trust this one or that one better. But I truly believe that they can be more complementary to each other rather than competing approaches. But I don't really handle all the details with it. But
yeah, I mean, my impression was that they were also built on the Davis-Chandrasekhar Fermi method. So
I believe,
like you say, I think they should be complementary. But...
yeah, to a certain extent, it does rely on a DCF, approximation. But what I've seen so far is that these two methods would actually produce similar results in very specific conditions.
Yeah, thanks.
All right, we've got a comment from Tony, and a question. DFC assumes that at minimum LTE exists. So do these dynamic regions actually achieve LTE, local thermodynamic equilibrium?
Oh my gosh. That is okay. Yeah, that's a good question. I don't know. To be honest, I'm not sure. It probably just does assumes some, the local thermal equilibrium. And that is why I truly believe that it's probably better to apply the DCF to more localized regions rather than a whole cloud, just in order to avoid this kind of um, this kind of situations in which, perhaps in a smaller region of the OMC1, for example, you could still say, okay, this is in LTE or at least, better than just doing it to the entire cloud. However, that is basically restricted by what is the object that you are observing and what is the resolution that you can achieve with your polarization data.
Okay. Are there any other questions from the audience?
Come on, guys, don't be like my students. I'm never sure whether I explained it everything, perfectly, or just they didn't even get anything.
So one thing I was a little curious about, your second topic, looking at M82.
Yeah.
It seems like you used the model to determine whether or not the magnetic field lines were open or closed at that 6.6 kiloparsec distance. Is there any plan to actually make a physical observation to verify that?
That is a good question, and the problem with that is that I'm not sure that the gas or the dust at that distance might be dense enough to observe with something like SOFIA Hot Plus. It might be possible to observe with radio, but I really don't work with that those details in particular. Yeah, the problem why we have to rely on those models, especially because it's so far from the really dense dust. At least with SOFIA, I don't think, or with far infrared polarimetry, I'm not sure we can measure it there.
Right. Okay. Well, unless there is another question lingering in the audience, then I think we'll give one final round of applause and thank you to Jordan Guerra. And yeah, I greatly appreciate having you here talking with us today.
Thanks for having me. It's great.
Of course. So with that, take care